Introduction, and thank you very much everyone tonight for joining me. I'm sorry I'm not Gillian. Hopefully she'll be able to talk to you once the first images have been released. I'm just going to share my screen and hopefully then the presentation, because I've got some spectacular images for you this evening. So I am Olivia Jones. I am a member of the MIRI European Consortium, which is led by Gillian Wright, and I am going to be using James Webb or JWST later next year to take observations of so many exciting science targets. And so we are in the countdown to launch now, as David mentioned. We are avidly watching it being shipped from its construction site in California all the way through the Suez Canal until it lands up in French Guiana in Kourou for launch. And this stunning video is a representation of what Webb will look like. It has this fantastic pink sunshade, which keeps it cool. And then as it turns around, that's the hot side of the telescope. As it cools around, this fantastic 18 segmented mirror, which is 6.5 meters across, comes into light. And I think it's stunning. So I hope you can all see that. So today, I'm going to touch upon two main areas: how the biggest telescope, the biggest eye in space, is built, and also I'm going to talk to you a little bit about the science revolution that JWST will enable us to have over the next 5-10 years, maybe even longer. So here is a little primer. This is everything the main key points from Webb that you need to know. And I'm saying Webb because I think over the next few years, if you hear it in the media, people aren't going to be saying JWST. It's going to be referred to as Webb in all press releases. So if we see it on the news, Webb, JWST, the James Webb Space Telescope are all the same thing. And so the key thing is, it is going to be the biggest telescope launched into space. And to do this, that means everything, because the mirror is 6.5 meters across, and that sun shield, that pink sun shield I showed you, is the size of a tennis court. So that means it has to be all folded up. And so that's what we're saying. It's a deployable infrared telescope. It works at infrared wavelengths. So that means heat radiation. It's not the same light that you see with your eyes. It sees at slightly longer wavelengths, the infrared. And because of that, it has a cryogen, which means the telescope needs to be cooled, of which the sun shield plays a large role. And very excitingly for me, and for very many people, its launch is on the 18th of December. I have been waiting for this point for about 10 years now. I think towards the end of my thesis, I wrote Webb will be launching in a few years' time. So 10 years later, or so, December 2021 is going to be the launch date. And then the next 6 months or so, I'll be one of the team members supporting its commissioning and making sure it's all ready for science operations. And it's going to be launched to a distance that's 1 million miles away from Earth, in a place called L2. And we hope that it will be a 10-year mission at least, if not a bit longer, which is joint with NASA, the European Space Agency, and the Canadian Space Agency. So that is the key facts on Webb. And Webb has an Imperial College connection. David already mentioned Gillian, Professor Director Gillian Wright of the UK Astronomy Technology Centre, and she has been one of the driving forces behind Webb, and particularly the mid-infrared instrument. And the Imperial College connection is that she did her PhD at Imperial College. So I just want to make sure one of the key drivers of the science and the engineering behind this fantastic mission was an Imperial College alumni. So just so you know, Gillian, this is Gillian, and I think she deserves a lot of plaudits, and you should see her face in this and hopefully her talking to you in the future rather than me deputizing. So moving on a bit, how do we win at astronomy? Well, the goal over many years is plotted here. We have the years of observation starting back from the 1600s all the way now to the 2000s, 2020s. And then we have a sensitivity improvement upon the eye, because for many, many years, obviously, the only thing you could see in astronomy was looking up at a beautiful night sky with your eyes with no light pollution, but that's as far as you could see. But then Galileo invented the telescope and could start seeing a bit further away seeing smaller objects. So the moons of Jupiter, as you move along, as eyepieces and technology improved, and optics improved, we could go further and further away. We could start discovering more distant planets, more distant galaxies. And eventually then, when photography came along, you could start to become more detailed. Instead of having to draw a picture of the night sky, you could start taking images and start processing them later. So that was a massive technological improvement. And then CCDs, charge coupled devices, meant it all became digitized. And again, that made life a lot easier for doing astronomy. And eventually, Hubble, we've come a long way in the few hundred years with Hubble, but with JWST, we are going to be breaking the scale. We're going to be able to see much further, much higher resolution, especially in the infrared, than ever before. So the best way to do astronomy is to keep building bigger telescopes. And if you can't build bigger telescopes, go to different wavelengths to discover new things. So this is how new discoveries are often made. And I want to prove to you that Webb is big. Before, I showed you this lovely animation of Webb in space, but this is Webb as it's in its final assembly stages. Here we have I love this picture. It's possibly one of my favorite pictures of Webb at the moment. You have this beautiful mirror with segments. And I hope you can see in this clean room, the people, to put it into a sense of scale, just how big Webb is. That mirror is bigger than my house. The sun shield, which is here now currently folded up, the silver and pink, is a tennis court in size. So this is a very large structure, and people are absolutely dwarfed by the size of this. And I have been lucky to see this in person, but not in its fully deployed state like this. But I absolutely love this image. To put Webb into context of other telescopes you may have heard of, Webb is big, really big. Hubble, I'm sure you're all aware of the stunning array of images that Hubble has produced, is about the size of a double-decker bus or so. And the mirror for Hubble is around 2.5 meters in size. And Hubble works primarily in optical wavelengths, so where our eyes are, a little bit in the near infrared, so in the same ballpark as where Webb will be, but it also works in the ultraviolet as well, where Webb will have no capability. And then the previous great observatory in the infrared was Spitzer. And I love this picture. Spitzer was tiny. I think of Spitzer looked like a race car. And it had a mirror, which was 85 centimeters across. One of these hexagonal segments is larger than the main mirror that was Spitzer. And Spitzer, unfortunately, ended its life as an infrared telescope on one of NASA's great observatories just a couple of years ago. So it's been doing excellent science up until then, but it has been switched off and ready for Webb to replace it and absolutely blow Spitzer results out of the water. And I've worked on Spitzer my entire career, so I'm very much looking forward to seeing these new discoveries, even though I'm quite sad that Spitzer is no longer operating. But this, I hope, really puts into perspective just how big Webb is. Now, you can't build one particular mirror in 6.5 meters across. It's not possible. So instead, you have to use this segment design. And this is a picture from NASA Goddard Space Flight Center over in Maryland in America. And this was ongoing while I worked at the Space Telescope Science Institute, which is about an hour or so down the road. And many people worked at both of these places. So each one of these mirrors was loaded in from this crane. You can see all the engineers. And that particular journey takes about a day to 3 days to put in a mirror segment. So one of my colleagues happily every single day took web stills from this image. Obviously it wasn't condensed down in space, and then printed it out and posted it on his notice board every time a new mirror went in to see the progress of Webb being made in real time. I think you'd be quite glad this evening we're not doing that, and instead we have a speeded up video. And I find it absolutely fascinating how the mirror, because the mirror has to be polished very carefully with no imperfections, so it has these mirror caps and that's why it looks black. And I just think it's absolutely stunning in how they take the crane to put the precise engineering in place and placing the mirrors without causing any damage. If you want to see that in person a bit closer up, this is one person putting in one of those segments. So as the segment's coming in with that crane, there's a person underneath taking all the wiring to make sure it's all set up to the rest of the telescope. And I just find this absolutely fascinating. So I think I've convinced you now we've built a big telescope. I hope we have. If anyone has any questions about that, you can ask me later if you're not convinced it's big enough. But I think we have a big telescope. So next thing is new wavelength coverage. I mentioned before that Webb is not going to be operating at visible wavelengths. They'll be operating in the infrared. And to give you a reason why this is this stunning image taken from Hubble of the Eagle Nebula. Maybe you've seen, especially the left one before, also known as the Pillars of Creation. So the reason why it's known as the Pillars of Creation in this left image is because this is actually a site quite nearby in cosmological terms of where stars are being born. And stars are being born in these pillars, particularly around here. There's these red dots, but they're hidden away. Most of the detail is actually within those pillars themselves over how stars are being born. And then on the other side, we've got the near infrared image. So we've now gone slightly to longer wavelengths. And what you can see here, it's the same field, everything is in the same size, all the objects are the same. But in what you can see here, that red star on this image is here, it becomes much brighter in the infrared. And you can start to see through all the gas and dust, which is in the visible. So as you go into the infrared, you can start peeling away layers. It's a bit like an onion. You can take off the top layer, you can see further into the structure. And that lets you do a large array of science of which you can't do just in visible wavelengths. So that's why going to other wavelengths, particularly infrared, is very handy. To put it in perspective, this is the same galaxy taken with Hubble, with its 2.5 meter mirror, and then taken with Spitzer in the mid-infrared with its 85 centimeter mirror. It's the same galaxy. What you may notice as you've gone to the infrared picture is you're seeing a lot where there's dark lanes, which are dust. In galaxies, these absolutely pop out. And in this image in the infrared, all that green you can see is called PAH is polycyclic aromatic hydrocarbons. It's a bit of a mouthful. And what that really is the smell of burnt toast. So if you see in these images anything around 8 microns, all this green is these PAHs. You find them in car exhaust as well, but you also find it on burnt toast. And that pops up in all these dark dust lanes. What you may notice is a difference in resolution and quality between the two pictures. The Hubble image is much crisper, whereas Spitzer is a bit more blurry. And what you will get with Webb, because it has a much bigger mirror, is comparable or even better quality images compared to Hubble. So that's a very exciting time. That'll actually do a lot more astronomy. So where these fit in the electromagnetic spectrum, the spectrum of visible light is here. Hubble operates from the ultraviolet to visible. Webb sits nicely in the middle between Hubble and Spitzer, operates in the near and mid-infrared. So we now have a big telescope, we're at new wavelengths, and that lets us study further into the early universe than is possible with current telescopes, because as you go further back in time, the wavelength of light becomes longer, called redshift. And so light from more distant sources that was, if you were close to them, would be in the visible wavelength, are actually in the infrared part of the spectrum. And as I showed in the first one of those comparison images, you can look deeper into regions where stars and planets are forming because it's less well absorbed. Infrared light is less well absorbed by dust. So we can see warm sources in these dusty environments easily. So one of these questions is to work in the infrared, which is heat radiation. How do you actually stop the heat from the telescope and the heat from the sun ruining your observations? And how does that there, because you have to be cold to be able to detect those heats, otherwise you'll just be observing yourself, and we definitely don't want that. If you've gone to this effort of building a stunning telescope, we don't want to be observing the telescope. Well, what we have to do is build the sun shield. And the sun shield is the equivalent of putting on factor 1.2 million sunscreen. So it blows your factor 50 on a very hot day out of the water. That's what the sun shield does for the telescope. And we also need to put it a long way from the sun. If it goes close to the sun, it'll be too hot to do these observations of these very cool, faint objects in the infrared. And I think the sun shield is a fantastic piece of engineering. It's slightly terrifying because it's made of this very, very thin material, which is folded up. So when we launch Webb into space, the sun shield is going to have to unfold and make its 5-layer structure. And as you can see there, to me, it looks rather flimsy. But amazingly, what it does is on the hot side of the sun shield, it's around 85 degrees Celsius, whereas that 5-layer sun shield goes into place, it becomes minus 223 degrees Celsius. So it does an extremely good job at taking away that heat. And I think that video puts it into perspective. Just to give you an idea of how big the sun shield is, where this is before the rest of the telescope had been integrated, the actual mirror part, this is just the sun shield. You can see the 5 layers unfolded, you can see how thin they are. And I hope you can also see in this top corner, a person next to the sun shield, making sure it's all unfolded correctly. I hope everyone can see this person up in this top corner, just to give you an idea of what the sun shield looks like when it's fully deployed. Just to put this in another, not quite the same close-up, but this is a perspective you can see. Again, it's always pink on the bottom and silver on the top, which helps part of the radiation. And again, this is now the same sun shield, but with the telescope being integrated in its final stage of building. And the reason why we have the sun shield is you have your light hitting the sun, and every single time, through every single layer, the heat hits it. Some heat gets transferred through, but the layers hopefully bounce out heat out the side. So by the time you get to the 5th layer, very little heat has made it to the far side of the sun shield. It's done its job effectively. And that's part design, part material of what it's made of. And that makes me very happy, because now I know I'm not observing my own telescope when I'm doing my observations next year. So we have the 2 sides of the telescope, the hot side and the cold side. So on the hot side, we have all solar panels to power the telescope, the communication arrays, the onboard computers, how you steer. And on the cold side, we have the mirror and the science instruments. So that's a little overview of the engineering behind Webb. Currently, as David said, and as we're all very carefully tracking, Webb is being shipped to the launch site as we speak. That's a 55-day journey, and we think it's currently just past the Panama Canal, although it could be a decoy. We're not, no one knows precisely it's that exact ship that we think it is. But you have to be very careful, because you don't want your expensive space telescope being hijacked by pirates. So it's quite, I don't think we'll know for sure until Webb has made it to the launch site that it isn't where it was in its journey exactly. But this is a very exciting time for me, and I hope you can tell that. And yes, launch is from French Guiana, which is just a little bit north of Brazil, at the European spaceport. And it'll be launched on this Ariane 5, not this particular Ariane 5 rocket, obviously, but on an Ariane 5 rocket, and launched 1 million miles away from us. So I hope you can see, this is just before it was shipped, the final part of the packing. So it makes it a bit different from your holiday packing. This is the opposite of what will happen in space. The sun shield, which is no longer in its 5-layer segments, is being folded up. The telescope has been brought down. There's a lens cap has been taken off. We don't want to keep that on for launch, want to make sure we can observe. And I love this. This happened not too long ago, and this video has only recently been released, of everything being compact into its launch configuration, ready for it to be shipped and put on top of the Ariane 5 rocket. And there we are, our massive telescope, all folded up into its most compact configuration. So I absolutely love that video. We just know it's all ready. So where are we? So the final mission analysis review has been done. It's currently in transit in its 55-day window. And then 30 days before launch, preparations will be in place for it to be put on the telescope. Once upon launch, it will take 30 days to travel the 1 million miles to a point called L2. And then after that point, during that transportation time, it'll be cooling down, it'll be unfolding. And after 6 months of doing some commissioning and making sure everything is ready for observations, the actual science operation begins. So we're very much in this final window of checking everything is being ready for launch, and the final countdown is on. To put this in perspective, there is quite a few checks to be going on. 7 days before launch, it'll be there sat and waiting on the launch pad. Everything will be checked 6 days to launch. And then in 1 day, the actual rocket will be placed on the launch pad. And it only takes 30 minutes after launch to be in orbit. So all the separations will go on. It's quite a quick, efficient process to be out of the Earth's atmosphere and into space and on its journey to L2. Now, I've mentioned L2 and this particular place a couple of times. L2 is a Lagrangian point, which is a bit complicated, but it's at this point 4 times the distance of the moon from us. It's always in a straight line between the sun, the Earth, and the telescope. So it will always follow the Earth around the sun, and it'll always be in this straight line. And this is a particular point around the orbit of the planets, particularly relative to Earth, which is very stable. And that means we don't have to have much energy on fuel. That means the fuel can be used to steer the telescope to look at different science targets rather than keep up tracking the sun. It's a very efficient orbit where you can place space telescopes, and many previous missions like Herschel and Planck have been at this L2 point around the sun Earth orbit. But it's a very important point. There's lots of missions there, and this is where Webb will spend most of its life before we may potentially put it off into space so we can make way for new missions. But I don't want to think about that. So we do have a question then, and how do you put a 6.5 meter mirror and the sun shield into a rocket which is 4 meters? And this is what we do. We have it all nicely compacted. Webb will be at this top point of the Ariane 5. And as I showed you before in that lovely packing video, it folds down in a very complicated way, of which then will unfold in space on the other side to make sure it fits in the top of the rocket and makes its science payload for observations. So I'm going to be very nervous upon this day. This is my own personal image of Webb when I got to see it just after all the mirrors had been put in place. Unfortunately, when I set out on my drive, the mirror was completely unfolded. And when I arrived, they'd folded it up from its glorious position into this compact configuration. So I only got to see a little bit of, I didn't get to see the full glory of Webb. I just got to see, but I still got to see it. So that made me very excited. And I was like a kid in a candy store at NASA that day. What this means though, in launch and in orbit, is this video here. This is what will happen. First, the antenna will unfold so it can communicate with Earth. Then the sun shield comes down, and way before we saw it, the mirror be lowered, it's now being raised. Eventually, because this needs to be done very carefully with the sun shield because the material is so thin and light, these sides will move out, making the sun shield taut at the sides. And then eventually the layers will start to increase. So it'll start to move out first, and then they'll start gradually, slowly but surely, increasing the height of the separation of the different layers of the sun shield. As this continues, we'll be starting commissioning operations, checking all the optics and electronics are working and communication is working. And then once the secondary mirror folds out and the sides unfold, Webb will be science operation ready, and we can start doing the rest of the calibration. And this happens while it is on, while it is still moving out to this L2 position. So, in the second point of the talk, I want to start moving on to the science that Webb will do. Webb has 4 main science instruments. Inside these instruments are NIRSpec, which is a spectrograph which splits up light into many different colours at very narrow wavelengths. I think of that a bit like the dark side of the moon cover of Pink Floyd, the rainbow. That's what spectrographs essentially do, but into very fine resolution. We also have cameras which take pictures of astronomical objects, so you may be more familiar with those. They're the very stunning pictures that you'll see on calendars or on various locations. And then we also have a thing called a chronograph. And this may seem counterintuitive, but a chronograph actually takes the light from your object and puts a big blocker in front of it. So it actually hides your main bright source of light, like my head is doing to this light in the background, and that lets you see the objects around it. And chronographs are fantastic, so you can see planets orbiting nearby stars. So they're the main type of tools we have on the 4 instruments. 3 of them operate at shorter wavelengths. These operate at 1 to 5 microns in the infrared. And here in that type of wavelength region, you'll see cool stars. So you'll see stars a bit like Betelgeuse. If you've ever seen the constellation Orion and you look carefully at the stars, you'll see one which is red. It had a great dimming event in the last couple of years, so you may have heard it on the news for that. Betelgeuse is a bit too bright for Webb to observe. In fact, it's very bright for Webb to observe, but stars like Betelgeuse in more distant galaxies is what those instruments are very sensitive to. They're also very sensitive to dust, and they can also, and galaxies. Whereas in the mid-infrared, the instrument built by Professor Gillian Wright, you can see into the mid-infrared. Now at this wavelength, you're starting to see disks around stars, and this is where planets are being born. You can see planets here, you can see comets, asteroids, you can see a lot of very cool processes. So for instance, some of them, the very first galaxies you'd expect to see in the mid-infrared, or in fact, where the very early stages of where star formation is occurring also occurs in the mid-infrared. So we have 3 instruments operating at the shorter wavelengths, and this 1 instrument operating a bit longer in the mid-infrared. And the mid-infrared instrument MIRI is the one which I'm personally involved with and working on. And actually, because it's operating at these slightly longer wavelengths than the others, it needs to be cooled even further. This is cooled to 7 degrees Kelvin. That is only 7 degrees beyond the temperature where atoms no longer can move. This is very cold. And this is MIRI, and it's wrapped up in all this thermal insulation to keep it cool as well. And there's many new technologies involved with MIRI to keep it cool. Previously, you used to have coolant, which then was a limitation on missions that used to run out, and so these instruments no longer worked. But there's a new technology called a cryocooler in MIRI so you no longer have to worry about your coolant running out for this. So MIRI can last as long as the rest of Webb, which is very exciting for me because this is where I like to do a lot of my science. And MIRI, many of the technology was built and designed at the UK Astronomy Technology Centre, which is where I worked. And recently, the European Space Agency has released this video. This shows where light comes in for the camera. It goes into the instrument, so it's seen the main mirror, and it's been put into the instrument, and it takes this path through the instrument itself. It bounces around. Then you have this thing called the filter wheel, this circular component, so you can change the wavelength of light you observe. And here's an example of it doing so. So this is how you get those stunning multicolored images by changing the wavelength of light you observe by rotating a filter wheel. And so I like this design of just how the optics work. So the 4 main science themes for Webb are the very first light in the universe, how galaxies are formed. As you're maybe familiar with, the Milky Way is this lovely spiral shape, but we don't actually know how many galaxies like this were assembled. And in fact, a lot of galaxies have collided with each other, as will our own Milky Way with the nearby galaxy Andromeda in many years. But that's another major theme, is how we actually get the universe around us and how do we see this. The birth of stars and planets. And also the final theme, main science theme, is exoplanets, so planets around other stars and looking for the origins of life around these planets. So briefly on the first light, as you go to earlier in the universe, light gets to longer wavelengths, which means going from optical light towards the infrared. So that means to see that very first light, you need to have your detectors in the infrared or mid-infrared. And here, I think this picture gives you a clue of how this has been changed over the last 30 years or so. From ground-based observatories, where the atmosphere interrupts your observations, and this shows the picture of how far away you can look. The Hubble Deep Field was taken in 1995, and that's, we got to see a bit earlier on in the universe. On the bottom here, it's time after the universe with a Big Bang occurring towards this side of the screen. The Hubble keeps going back and spending longer on that same patch of empty sky and seeing further and further away. And eventually Webb will be able to see around 20 million years after the Big Bang, which I think is absolutely fantastic in terms of the science discovery space. And this, if you want to put this in perspective, this is the Hubble Deep Field. And this is a simulated picture of the same patch of sky you will see with Webb. And what you may notice here is how crisp every single point of here on this image is a galaxy, and how crisp these images look. How you can see here, there's a bit more blurriness in the Hubble image, whereas in the Webb image, you will expect to see this very crisp picture. And in fact, anything that you can sort of see a structure will be closer to us. And these very, very, very tiny patches of light, especially these red ones, these dots, will be your most distant galaxies. So if you see an image like this released from Webb, what you want to be looking for is the really, really, really tiny red things, because that will be the most distant galaxies we'll have ever observed. I want to jump now a little bit to the other end of the scale in the nearby universe, with Webb trying to find life on nearby planets. There's a few ways you do this, but that's mostly using those spectrographs I talked to you about before. And what you want to do is you want to have your planet, and you want to take this around the star it's orbiting, and you'll measure its spectra on one side, and then you'll measure the star when the planet's behind on its orbit. And by doing that, you can actually work out what the atmosphere of the planet is, which I think is amazing. So you'll be able to look for lines, for instance here, oxygen, ozone, water vapor especially is something that we hope to be able to detect on other planets, and carbon dioxide and methane we expect to be in the infrared, where if they do exist on these planets, we should be detecting these signatures. So I think that's going to be a very cool discovery as well. And I'd expect to see that quite early on in the Webb mission. So looking for nitrogen, oxygen and carbon dioxide on other planets, which has not been able to be done before. And then in my own personal science, I study how stars are born and how what the origins are of the elements. So everything which isn't hydrogen, helium, lithium or beryllium, so all your gold you see, or the oxygen, carbon is made in the heart of stars, or as either when they're going through their normal life and then dying, or for more massive stars if they explode as a supernova. So this is where the origin of the elements are, and this is one of my own personal science interests. And what I do, I look at the star life cycle. So stars are born in this very dusty region in a star-forming nebula. Stars like our sun, which are counted as low-mass stars, go through this quite long life. They'll eventually become redder, expand, and they'll be making some mostly carbon type elements. And then they become these planetary nebula, they'll have a slow wind and gradually die. And this material will go back into the star-forming material, and it'll make a new star. And that has slightly more chemicals around it. A massive star does this process much quicker. By massive stars, I'm talking 10 times the mass of the sun, up until the very first stars, which could be 300 times the mass of our sun. So these stars are big, and these big stars live fast and die young. So they go through this process very quickly. So instead, they don't spend as much time on their normal life. Their life is quickly over. They become red supergiants, and red supergiants then explode as explode as supernova. They really go boom. And at that stage, the star itself can become a black hole or a neutron star. And we don't quite know how that forms. And hopefully Webb will be able to tell us that process if we look at the nearby supernova. Or the rest of the material goes back into this nebula, and this process continues and continues throughout the universe. And so what I do personally, sorry, I'm hoping I'm not, I'm indulging myself a bit now talking my own personal research, is I look at nearby galaxies, our own galaxy and the Magellanic Clouds, to see the birth and death of stars and the material within the galaxy itself. And by looking at galaxies nearby, we can see all the stars in one go. We can see all the stars are dying. We can see all the stars that are being born. And then we can actually extrapolate that. So we can take, look at galaxies with slightly less chemicals in them each time. And we can draw this line and try and work out what galaxies are like and how stars were born and how material formed in the early universe. So this is the science interest I'm going to do. And my personal science observation, I'm hoping will be taken early on in the mission, will be of a galaxy called 1 Zwicky 18. Now this is a very long way away. And currently our best picture of this galaxy is taken with Spitzer. And as you can see here, this is our very best image. It's not very good, is it? In all honesty, you've got two ginormous blobs and possibly a blob over here. And as you go to slightly longer wavelengths, this is all where MIRI will operate in the near infrared out to the mid infrared. In fact, those two blobs become one blob. The resolution becomes so poor. This is the top we know about of this galaxy at this moment. But what we do know from Hubble is it's not just one galaxy, it's two galaxies. These are the two blobs. We have this one blob here, which is in fact this bright blue, fantastic site of star formation. It's forming a star like our sun once a year about. So each year in this galaxy, a star like our sun is being born. And then it has this other component here, which we think is full of old stars. So those sorts of middle-aged stars, no supernovas in that part, where we expect we might see a few supernovas in this blue bit. And in the background are all galaxies. So I'm hoping that my observations with Webb will go from this to this. So if you see something looking like this in the near future, it's my picture. And then finally, it's not just imaging, it is spectroscopy. And so not just around other planets. This is an example of a spectra, back to that pillars of creation image, that red star I showed you before. Actually, when you break your light into these tiny little components, you can also see what material is there when a star is being born. So you can look for water, you can look for carbon monoxide. This is a very key feature of early star formation. Methane, ammonia, carbon dioxide, and then silicates. By silicates, I mean sort of a sandy material. So if you walk on a beach and you see tiny particles of sand, this is essentially the same as you get around stars that are being born as well. And so we'll get a wealth of information about the chemistry that's going when a star is being born. And this is an example of the 12 observing programs I will be involved in. I just love all these pictures. We have nearby galaxies, we have star formation, we have explosions of stars dying, and I can't wait for Webb to return images of these objects at stunning resolution, and I can show you that slide again in the future. So I'd like to leave you here on this picture of Webb, and I really look forward to having any questions. I'm sorry if it's been a whistle-stop tour on some of the science. There's just so much discovery space. It's a very exciting time. Thank you.
Well, thank you very much, Olivia. That's yes. We should be cheering you if we were not muted. Right. So questions. You can write questions in the chat at the bottom of the screen. At least on my version of Zoom, you'll find something called chat. If you click on it, you should be able to type in a question. If you want to ask your question in the traditional way of asking questions, when I ask you if you want to do that, you're very welcome to unmute yourself and say, give your question out loud. So the first question is from I think lie what to everybody, to everyone, is the mirror made of glass?
No, the mirror is made of beryllium. So this is glass is too heavy. That you have to be very careful about the weight when you're launching something into space. And glass, unfortunately, is very heavy. And also, glass is actually made of silicates, the sandy material, and you do not want to be observing distant sandy material with sandy material, because that will ruin your observations. So instead, we use beryllium, which is a very light material. It's not very common on Earth. The beryllium in this was mined in Arizona. So that's the main component of the mirror. And as you notice, this stunning gold picture, that beryllium then is got this very, very, very thin layer of gold. So that yellow is actually gold. So it's beryllium with a very, very, very thin layer of gold on the top. So you can collect as much light as possible. So in fact, I think all this gold you're seeing on this image is actually smaller than a fist size worth of gold. It is extremely thin across the mirror. So it's not glass, it's beryllium and gold.
So thank you. So Jen Sherman, do you want to ask your question out loud, Jen? If you do, unmute yourself. Okay, well, I'll ask it for you. Why was the launch site chosen? Olivia.
Hello. I wasn't allowed to unmute before, but I can. But yeah,
Okay.
so how and why was that launch site chosen, particularly as it's so far away from where most of it was built?
You want to have your launch sites close to the equator as possible. It makes life a lot easier for launching. Weight is a very key component of getting your payload from the ground to space. So the less you can spend on fuel, the more you can then actually spend on the instruments or whatever you want to launch. So the European Space Agencies, so what part of our community is based in French Guiana, and that's where all European Space Agency flights are launched from. So whereas NASA ones are launched from Florida, the European Space Agency launches from French Guiana. And the reason why Europe is launching it, the European Space Agency is launching it, is at the time of design, the Ariane 5 was the biggest rocket available. So you want to, as this is such a big telescope and compacting it is quite a challenge engineeringly, you want to have as much space as possible. So the Ariane 5 was the best rocket to launch Webb, and that's a European Space Agency design rocket. So that's why it's launched from French Guiana.
Okay. Ollie Ansel, would you like to ask your question? If you can unmute yourself.
Yeah. How long is the JWST and Hubble expected to stay operational?
So Hubble is got, I'm assuming you mean concurrently. Hubble is now into its 30s. I think it was launched in 92. I don't know. I was very young at that time. I'm trying to think, because I was there at Space Telescope when it was the 25th year of anniversary, when I met many of the astronauts who'd worked on servicing Hubble and launching it. Anyway, that's an aside. Hubble should be operational for as long as it can last. That's not a great answer, but it's currently getting older. It has gyroscopes which help steer it, and once those gyroscopes stop working, and as Hubble's getting older, that becomes more challenging. Eventually, at some point, it'll be turned off, and I imagine possibly during the lifetime of Webb. We don't know, because obviously you want to keep Hubble going as long as possible, and you want Webb to keep going as long as possible. But it's very much if Hubble has another computer failure or a gyroscope failure, then it won't be worth continuing operations. So hopefully they'll be operating together for quite a long time, but it depends on how well Hubble continues to last. The lifetime of Hubble was not meant to be 30 odd years. it was meant to be about a decade or so. So they're doing very well looking after it, but it won't last forever.
Thank you.
Yes, I can comment. I was present at the launch of Hubble, and I think it was 1989, but it was a long time ago, just like you said. And I'd like to move on then, and let's see who's next on the list. Victoria. Oh, wait a minute, hang on. Trying to do these in order. My screen is causing problems. Oh, yeah. Simis, do you want to unmute yourself and ask a question?
Hi, I'm in the spectroscopy diagram. Why do the different wavelengths produce different gases?
Yes, different gases emit at different wavelengths due to the molecules. Those features, if you think about it, most material is made in a lattice. Think of it like a bunch of Lego, or a bunch of if I had a dumbbell and I had two heavy things on either side, I'd be shaking a bit to keep the weight in order. And that's very much like a hydrogen atom or a water atom. You're shaking, and that shaking vibrations causes sharp peaks. As your shape of your material changes, how you vibrate or how the atom or molecule vibrates is slightly different, because you've got different weights in different places. And that slight differences affect the wavelength, the peak, where you're vibrating at. It's different energies and energetics. So, for instance, certain oxygen always sort of vibrates at a particular place. And so that line, then you can also associate to being oxygen. Or, carbon monoxide vibrates in this other particular way due to its structure, its lattice structure. And that operates in a different place. This is if it's in a nice lattice. If it's in a sort of haphazard lattice, it's more like sand. In its crystal form, sand can be a bit like sapphire. In fact, it is sapphire. It's sapphire, the red or alumina. It's fantastic. These amazing gemstones and ruby, they're all the same material, but in its sort of amorphous form, it has this big vibrational area because there's no nice structure to create this nice thin vibration, and they have this broader washed out feature. So where things are based on just the molecular chemistry of each individual thing. It's amazing. You're looking so far away to see the tiniest things, but they have this specific chemical composition and structure, so you know what they are. I hope that answered your question.
Thank you very much. Victoria Richardson, would you like to unmute and speak?
Hi, it's actually her husband. I
think it still counts.
I wondered how long it might be before we start seeing some imagery. Are we talking sort of months or 6 months? What do you think?
So once commissioning is underway, there will be some top secret pictures taken. I don't know what they are. I know people who do know what they are have been signing non-disclosure agreements. They'll be the first images released. So I imagine they'll be about 4 to 7 months after launch is when you'll see those first pictures.
Okay, well, we've waited a long time. We've waited 20 years, I think, so far. So a few more months, I guess we can stand it. Paul, your question? Okay, I'll read it. It's an interesting question. How much does the James Webb Space Telescope weigh?
I have no idea. I think you'd probably find that answer quicker if you Googled it. I don't know. I probably should know, but I honestly, I don't know how much it weighs. I'm sorry, I can't answer that.
Well, I've got a simple answer for you, Olivia. Once you're in space, it doesn't weigh anything, but you only weigh when you're in the force of gravity on the ground. And I think the point about L2 is gravity is balanced. But yes, no, that's an interesting question. Well done, Paul. You reduced Olivia to silence for a minute or two there. Okay, Rob, with a terrible, horrible question.
Oh no.
Rob,
Yeah,
please tell us your concern.
yeah. Obviously, as it's going to be 1 million miles away, with the Hubble, there were problems from the start, some of which I think needed astronauts to go up and fix it, but that's not really going to be an option with the Webb. So what is the plan?
Yes. Well, I think one of the reasons why Webb has taken such a long time to actually finish its design is to ensure it does not go wrong. We have absolutely shaken, rocked, rolled, cooled, done everything you can possibly think of to test Webb so it doesn't have those issues. So I think any test that could possibly been done has been done to ensure there's no issues. If it does get to L2 and there's a problem, I think we're going to have to get very creative. But I really hope we have spent this time and effort and energy testing all this, and so that won't be the case. As an aside, we have built some of these instruments to have redundancy. So if one particular part of that instrument's broken, we've got the same camera twice, for instance, in 2 different detectors. There's quite a lot of redundancy built into the telescope. So if something does go wrong, there is backups for much of it if possible. But please, I want it to be nice.
I'm sure you're right, and I hope so too. Yes.
Yes, I think it's a time when people will be crossing fingers and saying prayers. Yishai Renton.
Yeah, I was just wondering if what each layer of the heat shield was made out of, or if it was made of maybe different sort of materials. I don't know why, just to maybe let different amounts through.
No, it's all the same material. I think so. The pink is, I think, because it's made of silicon. That pink part. I don't know what the silver part is. I did look this up once, because I was quite shocked when I had this sort of pink, gold, and silver telescope. I wanted to know why it looked so colourful in all the artist impressions, and so I did make a point to find this. So I think it's silicon for the pink, but I don't know exactly what the silver is. So I can only partly answer your question, but it is all the same material in the sun shield. But it needs to be it's very, very light and very, very thin. If you think of it, if you run a marathon in that material, that they give you at the end, that very thin sort of, it's not that material, but the concept is very similar to radiate the heat away. And it's a bit more like cling film than that type of material, but it's lightweight. And that's the key point of it, as well as radiating away heat. So yes, a bit of silicon, but I don't know what the rest is.
Thanks.
Okay, Adam Ferrari. Go ahead, Adam. Okay, I think there's a problem with your sound, Adam. The question Adam has is, did you say, Olivia, that we don't know how neutron stars are formed, or did Adam mishear you?
We've never observed that formation occurring at any one point. I'm going to be observing the supernova 1987A. It's a supernova that went off in 1987. This is one of my 12 observing programs. And hopefully, it's been now many, many years since the explosion, and it's evolving. And we're hoping we'll capture the formation of a neutron star or a black hole in the very center of this, possibly for this particular object. We think, in theory, it's a neutron star, but the will be forming. But we don't know the exact physics because we never observed this process occurring at any point. We have theories. We see neutron stars at the side. We have stars that explode, but that actual formation process, seeing that in real time, will be stunning. And so, while we have an idea of how this happens, obviously, if you have an observation, you can test your theories and work out what is wrong with them and what is right with them. So we don't know exactly, and we don't know, for instance, if 87A will form a neutron star or a black hole, the boundary in mass, and I think that's a very exciting time.
Okay, Shoshana, would you like to speak up? Okay, I will read the question. Do you believe that the JWST will be able to prove events such as the Big Bang Theory? I think your answer is rather similar to the previous one in a way, isn't it, Olivia?
Yes, I think we have pretty good evidence for the Big Bang from the very first sort of discovery of the cosmic microwave background with the radio telescopes. So I think we're with missions like Planck and COBE, this cosmic microwave background at the very earliest stages of the universe has been seen. And so I don't think Webb will add much to the discovery space of that. What it is likely to do instead is when the very first stars switched on and started making energetics again, these really, really early stars are going to be massive, about 300 times the mass of the sun. And they have a lot of UV radiation. And that UV radiation will start impacting, this is very high energy, and it'll start interacting with all the hydrogen nearby. And that will reionize hydrogen, is the technical term. And I think that is what Webb will see, is hopefully see, is that moment when the first lot of stars are being turned on. So this is after the Big Bang, after the dark ages, where there's no stars, but that first light, and that's where I think Webb will be more powerful than the actual Big Bang radiation and the Big Bang itself.
Yeah, I think that was right. It's the first light of the universe that you're really seeking, isn't it?
Yes.
Okay. Ian Wynne-Jones, very worrying question. Do you want to ask it, Ian? Okay, I'll read it. What is the probability of failure? And of course, the question is complex because you've got many parts to the system. The rocket could fail. I mean, not that I could even think.
Thank you, David. I appreciate that.
I mean, there is risk analysis done, and probably one of the single point failures are the issue. Where do you lose something that you can't back up, that you can't have a second way of doing the same thing? And the launch is one of those. You don't have two James Webbs to launch, you've got one. And so the rocket is a potential single point failure. So it adds substantially to the risk, but the risk of an Ariane failing is extremely low because it is, I think Olivia indicated, it's a very old rocket. This will be one of the last launches of Ariane 5. And being on one of the last launches is the safest possible way to be launched by a rocket. Don't go on the first launch of anything. It's the first 5 launches are high risk, but Ariane 5 is a real workhorse now. It's been working for 20 odd years, more than 25 years actually, since the first launch of Ariane 5. So I would say with launchers, the risks cannot be got down much below the 1% level, and that's simply because there are very, very few launches. But I have to say, I don't even like to think about this question. This has ruined my evening having to think about it. And in fact, I was invited to go to the launch of JWST, and I just decided I couldn't stand the stress of seeing the rocket go up. I was responsible for providing that rocket, and I just didn't want the tension. I'll watch it on TV, but part of me will be going with it. Sorry, I've taken over.
No,
Olivia, but
thank you for answering that
something I
part.
deeply care about. Okay, I've lost my chats, but okay, let me go on. We probably need to draw this to a close. Yes, Paul, does the JWST use gyros similar to the Hubble Space Telescope?
Oh,
I mean, short of go ahead, Oliver.
the answer is no. It's much more of a juggernaut. I think of it like driving. Hubble, again, a bit like Spitzer, is a very nice, sleek, easily maneuverable rocket. With Webb, one of the problems is it's humongous, and so making it move around in space is quite a bit more complicated. Needs some fuel. That's what will limit Webb's lifetime, is the fuel needed to move. It's a bit like driving a big double-decker bus, maybe two double-decker buses compared to your nice, nifty Formula One car around space. And a lot of dealing with Webb's movement is momentum. You don't want to be observing the same patch of sky and start to spiral around. You want to go to one part of the sky and then get rid of that momentum and move back elsewhere. Otherwise, your lifetime of Webb will be drastically reduced. So it's not gyros, it's more fuel involved.
Olivia, that was wonderful. I think, I've got one final question from Keith Pearson. I'll read it out because I'm just about to let you off the hook, Olivia. Keith wants to know whether JWST, will it be flexible enough to quickly look at the source of gravitational waves? I suppose what he has in mind is if you detect a gravitational wave on the ground, you know where it is, you can triangulate. Could you swing JWST around to see what else is going on there? Is that your idea, Ken? So, Olivia.
I think it should be responsive. There is a mode called you can propose for time. So if you have an event go off and you're awarded time on Webb, you can trigger your observing time to say you want to point at a target. It may take a day or two because you'll have to make your file through the astronomy proposal tool. And actually that's the software that interacts with how things point. That will have to go and be checked. Then it'll have to be put in the queue and sent up the telescope, especially if it's out of a window where you can communicate. But it should actually be quite responsive if need be. And also your event has to be in a patch of sky where Webb can currently observe. If it's near the sun, you're not observing that target because Webb can't point towards the sun in any respect, otherwise it'll get too hot. So it has to be in a certain location of the sky at a particular time as well. But in principle, yes, you can do it if the conditions are right.
Okay, thank you, Olivia. That's I mean, really, I lost in admiration for the way you've covered the extraordinary engineering of this this telescope. I mean, it is really an amazing construction, and you've also shown us your enthusiasm for your chosen discipline of astronomy. For me, I wish you all the very best in the year to come. It's going to be one of the most exciting years of your life. I'm absolutely sure of it. But I think what's been really wonderful for us is for you to share some of your feelings, some of your emotions. We could live your experience with you. And I'm deeply grateful for that. And I imagine I'm saying that on behalf of everybody. And so I would ask everybody to unmute themselves, provided whoever's in charge of this thing allows it. And we give you a round of applause. So,
Great. Well done.
Well done.
very good, very good.
Well done.
Fantastic, thank you.
Bravo, bravo.
Yeah.
Well done.
Okay, I think that's a standing ovation, Olivia. Okay, well, if I can bring you back to the ground, to the world, to today, we've had a great, wonderful start for our year, for our academic year, and Olivia's done a wonderful job for us. Can I just give you a few bits of news? Our full next year's or this year's timetable for all of our events should be on the web, I think, tomorrow. We were hoping to move to in-person events at Imperial in the new year, but we will have some small in-person events before that. And so for members of Friends, you have to be a member to do this. We have next week on the 13th of October, a behind-the-scenes visit to the Centre for Transport Studies. So if you're ever worried about cars that drive themselves,
who are voting members. I mean,
sign up. We still have a space for a few people, and it will be in person, a live event, 6:15 at Imperial. You'll get details when you register. Behind the scenes at the Centre for Transport Studies. One of my deep regrets is I will not be there next week. I mean, this I think is an absolutely fascinating visit. But so there are a few places left. It's limited, I think, to 20 people. So please book immediately if you want to do it. Our next streaming event is from Melanie Windridge, one of our ex-students at Imperial, who now is at the Cullum Plasma Physics Fusion Center. She will be talking about the aurora, in search of the Northern Lights, and that's a fireside chat. So one of my more informal affairs, 4 o'clock in the afternoon on Friday, October the 22nd. And I will most certainly be there with you. So I'll see you then. Finally, our next live streamed public lecture for everyone, like we've had tonight, is something completely different. Developing novel RNA vaccines for COVID-19 and future pandemics. I think future pandemics almost worry me as much as launching JWST. But you can sign up for that in due course, 28th of October. So we've got a busy month ahead of us. I'll close by reminding you that if you can afford to make donations, that would be very much appreciated. They keep us running. But I'd like you all to thank all of you for coming this evening and sharing this experience of this, one of the great things mankind has done, in my view. Building a telescope to look back to the very beginning of time. And Olivia Jones, thank you so much for bringing it all to us once again. And with that, I will close, I think. Perhaps a final round of applause for Olivia, because she did well.